Carbon dioxide and oxygen are frequently measured in partial pressure units. Why? Well, first let's be clear that this is not related to the hydraulic pressure of the fluid in which the gas is dissolved. In fact, the reason is rather simple. The partial pressures being referred to when we talk of dissolved gases is nothing more than an equivalent gas phase partial pressure that would maintain the dissolved gas at its equilibrium value. In other words, the vapor phase gas is in dynamic equilibrium with the dissolved gas, and the equilibrium coefficient is called its solubility coefficient. This solubility coefficient is temperature dependent and also depends on the type of gas and the solvent. This model, like much of science, is an approximation. It is more than sufficient for this course, and you may remember it as Henry's law. So, by stating a dissolved gas's partial pressure, we are actually stating an equivalent partial pressure which would need to exist in a gas phase in dynamic equilibrium with the dissolved gas to maintain that concentration. This gas phase may or may not exist in reality. The advantage of expressing gas concentrations in partial pressure units is that it allows us to see the direction and strength of the diffusive driving force. Purely looking at a gas's concentration on two sides of a membrane does not tell us anything about the direction or magnitude of the diffusion. This is because two different solutions with two different solvents, for example blood plasma and fat tissue, may have the same gas concentrations on either side of a membrane, but are not in equilibrium because of very different gas solubilities. The partial pressure, on the other hand, is more consistent with thermodynamic behavior. A difference in partial pressures takes solubility into account via Henry's law and directly shows the direction and magnitude of the diffusive driving force for that gas.